Hey guys, welcome back to the channel. In our previous two videos, we solved this problem, factorial trailing zeros, in two different ways. The first way was kind of inefficient, or brute force method, but the second method is what you see right here, which is more efficient. Today we're going to run timing analysis on both methods and see why, as n scales, as this number becomes larger, one method is significantly better than the other method. Okay, so this was our first method right here, trailing zeros. Okay, and trailing zero 2 is our second method. Okay, so just from the code, let me go ahead and pull this guy up. Okay, so just from the code, we can see that trailing zero 1, okay, the first one, has a while loop in it, and he's also calling a fact function recursively. So as far as O of n timing analysis go, okay, this guy is something like, since he's calling recursively, a recursive call is about n log n, okay, because the recursive call keeps adding n times to the stack depending on how many times you call it. But however, our second method, okay, I think this is actually about n squared actually, okay, well, because we're calling it recursively, we're calling function and stuff, yeah. But our second method, okay, is just simply log n, or log n. And this is because it's a while loop that doesn't even run as many times as n is. If we pass 5, this is probably only going to run twice. Okay, and let's see it. So using this notebook, I like to use Google Colab. It provides you a function called %timeit. Okay, so I'm going to call this on both functions, trailing zeros 1 and trailing zeros 2. Okay, so for n equals 5, let's see what it does. So what it does is it runs the loop 1,000 times, and after 1,000 iterations, it kind of gives you the average. Okay, so for the first guy, he runs in 900 nanoseconds. The second guy is in, let's call it 3 nanoseconds. Okay, 300 actually. So the second guy too is 3 times as fast for n equals 5. Okay, now let's cut to n equals to 15. Okay, this is gonna take a while to run, so I'm probably just gonna cut through the video and just not waste you guys' time here. But actually, let's start with n equals 10. Okay, let's see. Keep in mind that this is 3 times as fast. I'm just gonna copy this right here, call it right here. Okay, and say n equals 10. Okay, keep in mind this was for n equals 5. Okay, let's go ahead and run this guy. So for n equals 10, okay, one guy takes 2 microseconds, the other guy takes 200 nanoseconds. So if we convert both of them to microsecond, this is going to be 0.2. So this is going to be 0.2 microseconds, right? And this is 2 nanoseconds. So literally, this guy is now 10 times faster. Here he was 3 times faster. Here he's 10 times faster. We just doubled n, okay? It went from 3 to 10 times, so pretty much double. Okay, now let's go n equals 20. Actually, let me do it in a new tab so we can see what the previous guy is and see how it kind of scales. Okay, let's go n equals 20. So now for n equals 20, okay, what we see is this guy's 300 nanosecond, while this guy's 4 microsecond. So literally, this guy's time has pretty much doubled, but this guy didn't double. Okay, this guy just went from, I'll call this 300, this guy pretty much stayed the same, 300. Okay, now let's go to n equals, so you see my point. Okay, this guy is now 12. Okay, previously he was 4. Okay, so I went 5 times from 1 microsecond, he's gone to 12. Okay, so for a 5 times increase in n, this guy made a 6 times increase. Okay, but however, this guy stayed roughly the same, 300, 350, roughly the same. So you guys kind of see my point. Okay, the reason why this method is so much better than the previous method is because as n scales, this guy he's a log function, so meaning he has a cap. A log function looks something like this. Okay, let me go ahead and take all these guys out. Okay, so a log function is just an inverse of an exponential function. Okay, if this is an exponential function, okay, this is e to the x, whatever. Okay, a log function is its inverse, it's something like this. Okay, let's just say ln natural log, since we're using e, ln of x. So all this means is that there's always a asymptote here where, okay, early he ramps up for as n starts increasing, he increases fast, almost exponentially, or well, actually almost linearly actually. Then at the point he caps off, where as n goes higher, he doesn't increase much, he just stays that way. Whereas the other guy, which is a linear function, the second guy, he goes something like this, because the second guy is n log n, and n is the higher guy, so he goes something like this. So this is pretty straightforward. If you have a linear function and a logarithmic function, for small n's, okay, and the word small is relative. For small n's, okay, it will look like the log function is performing worse, okay, because it's increasing as far as timing complexity. But as n keeps scaling, a linear function will always grow higher than a log will, which is why we always prefer BO equals to a log function better than a linear function. That's it for the video, guys. I hope this was helpful, and I'll see you guys in the next one.